Wireless LAN antennas. Now the signal strength, the connectivity, and the security of a wireless LAN can be affected tremendously by the different types of antennas that are used within a wireless LAN. And that's exactly what we're going to learn about in this video. Now in order to select an appropriate antenna for our wireless network, we need to know how the radio frequency from a wireless antenna is propagated from the antenna. So to learn about that, we're going to learn about the different antenna categories and the different types of antennas that fit within these categories. And we'll learn about key antenna concepts such as polarization, gain, beam width, and free space path loss. And then we'll finish things off by learning about the best location where antennas should be installed and some antenna installation tips as well. So grab a beverage, get a snack, and get an antenna because we're going to get started here. First off, let's learn about the different antenna categories. Now there are three general categories of antennas that are used within a wireless LAN: omnidirectional, semi-directional, and highly directional. Let's learn more about these different antenna categories. First, starting with omnidirectional. And first off, what is an omnidirectional antenna? Well, to learn about that, let's bring up another whiteboard. Now, the key definition of an omnidirectional antenna is that it radiates its RF signals in a 360-degree pattern along a horizontal plane. So meaning the signal radiates in all directions. Now we can see what the radiation pattern of an omnidirectional antenna looks like by bringing up another whiteboard. So as we see here in this illustration, the radio frequency signal is radiating out in a 360-degree pattern, and it's radiating out equally in a 360-degree pattern. But we have a bit of a donut shape here. It's not a perfect sphere. In the middle of this illustration, we have an antenna axis, which is serving as the antenna. This is the point from which the RF signals radiate. And a very common type of omnidirectional antenna is a dipole antenna. We'll take a closer look at a dipole antenna in just a moment here, but dipole is spelled D-I-P-O-L-E. So this axis is going to serve as our dipole antenna. And with a dipole antenna, just because it's an omnidirectional antenna, the RF signal radiates equally in all directions around this axis. So it's radiating out in a 360-degree pattern along a horizontal plane. However, if you notice, though, that the RF signals don't radiate along the length of the antenna itself. And because the RF signal doesn't radiate along the length of the antenna itself, that's what creates this shape that we have here. It's kind of a donut shape, or kind of the shape of an apple, where you have a dimple on the top and then a dimple on the bottom. So one of the takeaway points from this is that an omnidirectional antenna, such as a dipole antenna, radiates equally in all directions around its axis, or around the antenna itself, but it doesn't form a perfect sphere. Now, a theoretically perfect antenna would radiate its RF signals equally in all directions to form a perfect sphere, or a perfect ball-shaped radiation pattern. And this is called a isotropic radiator, and that's spelled, I'll just write that down here, I-S-O-T-R-O-P-I-C, and then it's radiator, R-A-D-I-A-T-O-R. Now, we can't create an isotropic radiator antenna, but an example of this would be the sun. The sun is an isotropic radiator that radiates its power equally in all directions simultaneously. So we don't have the technology to create an isotropic radiator antenna, so we've done the next best thing, and that is to create an omnidirectional antenna that radiates its power in a 360-degree horizontal fashion, but not 360 degrees vertically. Now, another reason why it's important to know about the isotropic radiator is that it's also used in antenna gain measurement. Now, the measurement of how well an antenna focuses its signal is measured in decibels relative to an isotropic radiator. So, antenna gain measurements will be measured using this symbol, dBi, which again is decibels relative to an isotropic radiator. And dBi is measured or computed by comparing the output of the antenna to a theoretical isotropic radiator antenna with a dBi of 0. And the higher the dBi measurement, the higher the power level of the antenna. Also, something to note is that if we use an omnidirectional antenna that has higher gain, the radiation pattern starts to get squeezed. It starts to get flattened out horizontally, so it looks less and less like a donut and more like a pancake. And the result of that is that the radio frequency signal gets very concentrated and it gets very flat, and a result of that is that it extends out further. So right now we see that we have this kind of sphere-like shape, or a donut-like shape, if you will, and it radiates out pretty far. But if this signal were to get compressed by using a higher gain antenna, the signal would get flattened out, but it would travel further out, and as a result allow us to provide greater distance for wireless connectivity. However, you have to be very careful as to the positioning of the antenna and the wireless clients. So, for example, if you were to mount a high-gain omnidirectional antenna on the ceiling, and if you have a really high ceiling, you can have problems with the signal reaching the user's computers, which are down on the floor. And so because the signal is traveling horizontally, and that signal is going to be traveling closer to the ceiling than on the floor, the users could get spotty wireless connections, or they may not be able to get a wireless connection at all. So your typical wireless access point has a low-gain antenna, and if you leave that mounted somewhere on a desk or a cabinet or somewhere closer to the floor, that signal will travel horizontally along the floor, and it'll also travel a little bit above the floor. So if you have a multi-story building, it'll travel along the floor, it'll travel a little bit above the floor in the higher floor, and it'll travel a little bit below and the floor right below it as well. So in a nutshell, we're going to use an omnidirectional antenna when we need to provide coverage to wireless clients in all directions around a horizontal axis. So most typical low-gain wireless access points should be placed in the middle of a large room. So if you need to reach all the corners, so on a 360-degree radius, it's best practice to place that wireless access point and its low-gain antenna in the middle of a large room. And so omnidirectional antennas, such as a dipole antenna, are excellent for coverage in warehouse areas where you need to cover a large area in a 360-degree horizontal fashion, or an office floor where you need to, again, reach all corners of that office floor to provide a wireless LAN for the workers in that office floor. So let's bring up another whiteboard and take a look at some typical dipole antennas, which again are omnidirectional antennas. The first antenna type that we see here is a typical type of dipole antenna that you'll see in the back of wireless access points. And again, this is a low gain antenna, and ideally you want to place the wireless access point in the center of a room to distribute the radiation pattern to all corners of a room. Now, oftentimes it might be difficult to place a wireless access point in the middle of the room at floor level. So oftentimes what companies will do will place the wireless access point up in the ceiling. So in most companies they have ceilings that consist of, first off, the structural ceiling of the building, and then they have a suspended or a recessed ceiling, and they'll place the wireless access point up in this area here. And just a little FYI, this space that we have up here in the ceiling space here, where oftentimes you've got computer cabling, the heater ducts, the air conditioning ducts, and all that kind of stuff. This space is called the plenum, P-L-E-N-U-M, and you have to get special plenum cabling that is fire retardant cabling if you're going to place cabling up in that space. But if you place your wireless access point up in that space, the problem that we have is that a lot of the RF signals are being radiated horizontally in this space. Certainly these signals will go down, but how far depends on the gain of the antenna, how much resistance or impedance the ceiling tiles are going to cause for the radio signals to pass through. So in those situations we're going to use a ceiling mounted antenna, place that in the middle of the room, and as a result of that, that'll allow for broad coverage for 360 degrees from corner to corner of that office floor, and the RF signals will be able to reach down to the floor through the use of a ceiling-mounted antenna. So again, this ceiling-mounted antenna will be mounted underneath the tile, so that'll be exposed. You'll be able to see it, but it's relatively aesthetically pleasing. You might think it's just a sprinkler for a fire system or some fire alarm detector or something like that. It's pretty benign looking, if you will. Now, if you need to provide wireless coverage outside in a campus-like environment, say for example for a college campus or a corporate campus, we could use a dipole antenna such as these that we have right here. These are high-gain dipole antennas, and similar to the location practice for wireless access points, where we want to place the wireless access point in the center of the floor, we'd also ideally want to place the outdoor high-gain dipole antennas in the center of our campus environment, so to allow for the RF signals to radiate to all corners of the campus, if you will. And these type of antennas are usually mounted on some type of tower structure or on the top of buildings. Now, in addition to omnidirectional antennas, there are also semi-directional antennas. Let's bring up a whiteboard and learn about this category of antennas. Now, antennas that fall into this category, what they do is they concentrate the radio frequency energy into a cone shape, which is also known as a beam. So in contrast to a dipole antenna where the radio frequency is transmitted on a 360-degree horizontal plane from the antenna, with a semi-directional antenna, the majority of the energy, the radio frequency, is transmitted forward versus in a 360-degree, so we've got a directional, if you will. These type of antennas are also referred to as unidirectional. The majority of the radio frequency is transmitted in a single direction, and that single direction is forward, or the direction that the antenna is pointed in. Now, some of the radio frequency energy is still propagated in the back here, but not nearly as much as a dipole antenna. So to get a better understanding of this, let's take a look at a classic example of a semi-directional antenna and see how the radio frequencies propagate from this antenna. So to do that, we're going to bring up another whiteboard here. So in this illustration, we're looking at a classic example of what's called a Yagi antenna. Yagi antennas have been around since 1928. They've been used for many different purposes, from radio to TV, now to cell phones and wireless LANs. Now, a basic Yagi antenna, such as we have in this illustration, contains three main elements: a director element, a driven element, and a reflector element. Now, this middle element, called the driven element, is called this because it's actually a dipole antenna, and it's the only element that's connected directly to the radio, so hence it actually drives the whole antenna. Now, in contrast, these two outer elements, which are also referred to as parasitic elements, they work with the radio frequency that is being driven by this dipole antenna. So, for example, the reflector element actually reflects the radio frequency energy. In contrast, the director element directs the radio frequency energy. So these parasitic elements, the director and the reflector, they're not connected directly to the driven element or directly to the actual dipole antenna. So instead what they do is they pick up the radio frequency energy from the dipole and then they re-radiate it in such a manner that it provides a direction for the energy. Now, this direction by and large is a forward direction, but as I mentioned just a moment ago, some of the energy still does propagate out the back though. And we can see that by bringing up another whiteboard which illustrates the coverage area for a typical Yagi antenna. So in this illustration we see that the majority of the radio frequency energy that's emitted from a typical Yagi antenna is going in the forward direction here. And this radio energy, this radio frequency energy that's going in the forward direction is referred to as the major lobe. Now, in addition to this major lobe of radio frequency energy that's coming out at the front of the antenna, if you will, we also have radio frequency energy that's being emitted out the side of the antenna and out the rear of the antenna as well. And this energy that's coming out the side and the rear is referred to as minor lobes. And these minor lobes are caused by radio frequency energy that's radiating from the reflector portion of the Yagi antenna. Now the width of the major lobe, or the beam that we have here, so the width portion would be from here to here. Now this can be increased or decreased depending on how many directors we have. So for example, if a Yagi antenna has additional directors, what's going to happen is that is going to increase the directivity of the beam, because by adding additional directors, what that's going to do is that it's going to increase the gain. By increasing the gain, that's going to reduce the beam width, and by reducing the beam width, that's going to give us more forward direction here. So similar to a high gain dipole antenna, which flattens out the radio frequency energy, and as a result of that flattening out of the radio frequency energy, by having high gain, that allows the radio frequencies to travel a greater distance. So remember, with the dipole antenna, with a low gain antenna, the radio frequency energy looks more like a donut. But when you add high gain to it, or when you increase the gain, that flattens out the frequency and allows that frequency to travel further distance. Well, that same example holds true with the Yagi antenna as well. When we add additional directors, that increases the gain, that flattens out the width of our major lobe, or the beam width of the radio frequency energy that's being emitted from the Yagi antenna. And by flattening out and increasing the gain of that antenna, the radio frequency that's being emitted from the antenna travels further, and it travels further in a more pointed direction. Now, Yagi antennas are typically used for short to medium distances to provide building-to-building bridges. So, for example, if you need to provide a bridge between one building and another building of up to about 2 miles, then a Yagi antenna is an excellent antenna for that purpose. But they're also used in other capacities as well. Because of the directivity, if you have a long hallway that you need to transmit a radio frequency energy down, a Yagi antenna is excellent for that, where we place the Yagi antenna at one end of the hallway to allow the radio frequency to be transmitted in that corridor or the length of the hallway. They're also good if you want to place it in the corner of an office building and have that radio frequency emitted out from the corner. So let's say, for example, you need to provide wireless LAN coverage down a very long corridor. And one method for providing that coverage is simply to use lots and lots of wireless access points. And the reason why you'd probably have to use lots and lots of wireless access points is due to the fact that most wireless access points come with an omnidirectional antenna. And in an indoor environment, these antennas usually have a range of about 150 feet in length. So that could end up costing you more money than really what's required. If you use a wireless access point with the Yagi antenna, which gives you this forward directional beam width of the radio frequency energy at a greater distance, you could use fewer wireless access points, thereby saving some money and giving you the wireless LAN coverage that you need for the corridor. So again, in addition to using Yagi antennas for providing point-to-point connectivity for wireless bridges between two buildings, Yagi antennas are excellent for providing wireless coverage down paths, so down pathways or down long aisles in a warehouse or in rail yards or even retail stores or manufacturing sites. So now you might be asking yourself, well, which side of the antenna emits the major lobe and which side emits the minor lobe? Meaning, what direction do I point this thing in? Well, to answer that question, let's go back to our previous slide here. And you can answer that question by simply the name of these components here. The director is the element, remember, the parasitic element that actually provides the direction of the radio frequency energy. So this is wherever the director is, that is the direction that you want to point the Yagi antenna in order to provide your wireless coverage. So basically, the major lobe of the radio frequency that's being emitted from a Yagi antenna flows in the direction of the director, which is right here. And if you notice, the director is a little smaller than the driven element, which again is the dipole antenna, and the reflector, which is in the back here, is a little bigger than the driven element. So typically the reflector is about 5% larger than the driven element, and the director is about 5% smaller than the driven element. And again, the more directors that we add to a Yagi antenna, that will increase the gain of the antenna, and as a result will decrease the beam width, or that cone will get the cone pattern, or the coverage area will get narrower. However, the length of the coverage area will increase by adding more directors. So that's the 1, 2, 3s of a Yagi antenna. Let's take a look at some pictures of a Yagi antenna that's used within a wireless LAN scenario and other types of semi-directional antennas by bringing up another whiteboard here. So first off, we see a couple examples of Yagi antennas. The first one we should be very familiar with. This portion right here, we see multiple, what are they called? That's right, directors. We have multiple directors, and that, by using multiple directors, again, that increases the gain of this Yagi antenna. In the middle portion right here, this is called, you got it, you nailed it, that is the driven element. That is the dipole antenna. And lastly, we have at the back, that's right, that is the reflector. Now, you'll find that most Yagi antennas that are used for wireless LAN capacities, remember, this antenna type can be used for a lot of different capacities, such as TV and cellular capacities. However, a Yagi antennas used for wireless LAN capacities will typically look like what we see right here. We actually have a cover over the driven element and over the reflectors and the directors to provide some protection against the elements, protection against wind and rain and so on and so forth. Now, another very popular type of semi-directional antenna is called the patch antenna. And as you can see here, there are outdoor and indoor versions of the patch antenna. The indoor versions are typically used with access point to give a little more directionality for that access point, and they're a little more aesthetically appeasing. We can hide these or have them blend into the surroundings by painting them, and they're relatively nondescript type of antennas. However, they're not as directional as a Yagi antenna. Let's take a closer look at this by bringing up another whiteboard that illustrates the radiation pattern of a patch antenna. So we can see here from this illustration that this being the patch, the actual patch antenna, we can see that the radiation pattern coming from this patch antenna is more of a kind of like an egg shape or an oval shape. And we have a little bit of a minor lobe coming out the back here, but this is the major lobe in the forward direction of the patch antenna. So in contrast to a Yagi antenna, which has a radiation pattern which is in a cone shape, this radiation pattern in a more of an oval or an egg shape still gives us forward direction for emitting the radio frequency energy from the antenna. It still can be used for short range wireless bridges and indoor capacities, as I mentioned, but it doesn't give us as much of a pointed direction from this type of antenna than a Yagi antenna has. Now, similar to the Yagi antenna, though, if we were to use a high-gain patch antenna, that would certainly flatten out the radiation pattern of the patch antenna, but not nearly as much as when compared to a high-gain Yagi antenna. Now, in situations where we need to provide a very long-range point-to-point wireless bridge, then we're going to have to up the ante, and we're going to have to use a highly directional antenna. Let's bring up another whiteboard and take a look at some examples of highly directional antennas. Now, the most common type of highly directional antennas is the parabolic dish antenna, and as you can see here, it looks very similar to a satellite TV dish. And again, these are used to provide very long-distance point-to-point communication links for a wireless bridge, and these can typically transmit up to distances of 25 miles with a very high-gain parabolic dish antenna. Now, the disadvantage of using a parabolic dish design is that in very windy areas, these type of antennas can really get knocked around quite a bit. So in windy areas, a better solution is the grid type of antenna. So again, it's still very highly directional, can still transmit distances over very long distances, but it has a wire mesh design, and that design allows the wind to pass through the dish instead of knocking the dish around. And let's bring up another whiteboard to take a look at the radiation pattern of a highly directional antenna so we can compare and contrast that to our previous two antenna categories. So we can see here, right off the bat here, this is a very concentrated, very narrow beam width. Now, because the radiation pattern of a highly directional antenna, such as a parabolic dish antenna, is so very narrow and so very concentrated, it requires that the two antennas, the point-to-point antennas have line of sight and that they be aimed very, very accurately. So a typical beam width of a high-gain parabolic antenna is only about 8 degrees. In contrast, the beam width of a high-gain Yagi antenna is about 30 degrees. So with 8 degrees, you don't have that much wiggle room. There isn't that much broad coverage area to work with a high-gain antenna. So it needs very accurate aiming for the point-to-point communication for your wireless bridge. So again, highly directional antennas are not used for providing a wide coverage area, but instead they're used to provide a long distance, highly focused transmission of data from one point to another point. Now, in addition to knowing about the radiation pattern of an antenna to help you choose the appropriate antenna for your needs, you also need to know about some of the concepts behind the electrical specifications for an antenna. So, for example, when you look at any given antenna, most vendors will have electrical specifications such as the frequency range. For example, does it operate in the range of 2.4 gigahertz, the impedance level, the gain level. But in addition to those type of specifications, there's other specifications you'll see such as polarization. Let's bring up another whiteboard and learn about some of the antenna concepts that you'll run across when you're purchasing antennas. Now, in addition to what we've already learned about antennas, it's very important to understand the concepts of antenna polarization, beam width, and free space path loss. So first off, what is polarization? Does that mean we're going to go up to the North Pole and place an antenna up there? No, it does not mean that. Let's bring up another whiteboard and see what it actually does mean. Now, in a nutshell, polarization basically means whether or not the antenna is in a horizontal or a vertical position. But as you can imagine, there's a little more to it other than that. Now, the radio wave that is being radiated from an antenna actually consists of two fields, an electric field and a magnetic field. The electric field is called an E-plane, whereas the magnetic field is called the H-plane. Now, the E-plane runs parallel with the antenna. In contrast, the H-plane runs perpendicular to the antenna. And it's the E-plane and the position of the antenna that we're most concerned about. So let's bring up another whiteboard and see how these two aspects come together and see why polarization is important to antennas. Now, a horizontal polarization simply means that the electrical field is parallel to the ground. In contrast, vertical polarization means that the electrical field is perpendicular to the ground. So in this example right here, we see vertical polarization where the electrical field, again represented as the E-plane, is perpendicular to the ground. In contrast, a horizontal polarization where the electrical field is parallel to the ground or parallel to the Earth's surface. So here's the 1, 2, 3s as to why antenna polarization is important to know about. Number one, you need to ensure that the transmitting and receiving antennas are both either horizontally or vertically polarized. So for example, if you have a transmitting antenna that is horizontally polarized, but the receiving antenna is vertically polarized, well, those two antennas are going to have a hard time, those two radios with those antennas are going to have a hard time communicating with each other because of the different polarization and how the E-plane will be traveling on different planes, either parallel or perpendicular to the Earth's surface. So a typical example of polarization problems can occur if you have a wireless access point with its antenna vertically polarized, and oftentimes those antennas are just standing straight up. They are vertically polarized and perpendicular to the Earth's surface. In contrast, the users with a laptop computer, which have a PCMCIA wireless network adapter, their polarization of their antenna is horizontal, is running parallel to the Earth's surface. So you're kind of butting their heads there with the antennas. One is horizontal, the other one's vertical, and it's no wonder that laptop users often experience poor reception, dead zones, drop connectivity just by moving their laptop around a little bit. Now, in order to provide good coverage, the wireless access points typically need to have their antennas vertically polarized. However, if you have a laptop user that is just having all sorts of problems with wireless connectivity, you could simply get a wireless network adapter that has a little attachable vertically polarized antenna, or you can get these little antennas that connect to a PCMCIA card that can attach to the back of or mount to the back of a laptop computer, typically with a little Velcro strap to give you a vertically polarized antenna, and that will greatly improve reception and connectivity for that laptop user. Now, in addition to the horizontal and vertical polarization of a wireless antenna, we also have to take into account the radiation pattern on a horizontal and vertical level as well. Let's bring up another whiteboard and learn more about this. Now, the beam width is really just the width of the radio frequency signal that the antenna transmits, both on the horizontal plane and on the vertical plane. And there are specific words for these two planes here. The azimuth beam width is the pattern of the radio signal that is on the horizontal plane. In contrast, the elevation beam width is the pattern of the radio signal that is on the vertical plane. And these beam widths on the horizontal and vertical planes are expressed in degrees. So, for example, if you were to purchase a 2.4 gigahertz Yagi antenna, the beam width of that antenna might be an azimuth of 55 degrees with an elevation of 40 degrees. So there's a couple of reasons why this information is important to you. Number one, when you go to purchase an antenna, it'll give you these specifications. It'll give you the degrees of the azimuth beam width and the elevation beam width. And so you need to know these terms when you're purchasing wireless antennas. And they'll often show you a plot in degrees of these two beam widths. So let me bring up an example of an azimuth beam width, which again is on the horizontal plane of a typical dipole antenna. So again, the dipole antenna radiates in a 360-degree pattern on the horizontal plane. So another way to think of the azimuth or the horizontal plane is that you're taking the perspective, the bird's eye perspective, if you will, where you're looking from top down. You're above the radiation pattern and you're looking down at it. And just as a little aside here, the software that I've used here to generate the azimuth of a dipole antenna is free software. It's called 4NEC2, and it's used to simulate the patterns, the radio frequency pattern, both on the horizontal and on the elevation plane. Again, the azimuth and the elevation plane. And you can download this from this website. Let me bring it up here. And you might want to pause the video to jot this URL down. And this is the file that you're going to download. 4NEC2 version 541.zip. That is the most current version as of the making of this video. And yes, for you Linux gearheads out there, there is a Linux version as well. This is the Windows version. So let's go back to our slide here. Now, I said that there's two reasons why you need to know this information. We've already discussed the first reason. The second reason is to ensure that you purchase the appropriate equipment. So let's say, for example, you need to provide wireless coverage down a long hallway, and you also need to provide wireless coverage for the floor that's above the antenna and a floor that's below the antenna. Well, if you get an antenna, let's say, for example, you get a semi-directional patch antenna that's very, very high gain, what's that high gain going to do to the radio frequency pattern? That's right, it's going to flatten it out. And if that radio frequency pattern is flattened out too much, or the beam width is flattened out too much vertically, and it's spread out, the beam width is spread out more on a horizontal level or at the azimuth, then you're going to have a very, very difficult time providing wireless coverage for the floor above and the floor below where you place the antenna. So, for example, if you were to purchase a high-gain patch antenna that only provides an elevation beam width of 30 degrees, that's not going to be enough coverage for the floor above and below where the antenna is. So instead of purchasing a single antenna, you may have to purchase two low-gain antennas to provide enough coverage down the long hallway, down a long corridor, and to also provide enough coverage for the floor above and below where the antenna is located. So you might find that you'll have to get an antenna with an elevation beam width of about maybe 80 degrees. So really what it comes down to is that it's really essential to know the radio frequency coverage area as expressed in the azimuth beamwidth in degrees and the elevation beamwidth in degrees to determine, number one, what type of wireless equipment you're going to need, and number two, how much wireless equipment you're going to need for your wireless LAN. And one last thing you're going to need to take into consideration is something called free space path loss. Let's bring up another whiteboard and learn about that. Now, free space path loss, or what's typically known simply as path loss, is simply the fact that the signal strength, the radio frequency signal strength, gets weaker as the signal gets wider. So as it's getting wider and wider and wider, it's decreasing and decreasing and decreasing in signal strength, which is pretty straightforward, which essentially means that the further away you are from the wireless access point, the weaker the signal gets. So let's say you've got some wireless clients that are at the edge of the coverage area for a wireless access point, and they are complaining that they can't get connected, or the connection is too slow, or it gets dropped, and yada, 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 yada. And your boss says, fix this problem. Okay. So before you run out and just get any old antenna, though, there's a little rule that you can go by to help choose the appropriate antenna, which is going to give you enough coverage area, but not too much coverage area for your needs. And that rule is the 6 decibel rule, which states that for each 6 decibel increase in EIRP, which is the equivalent isotropically radiated power, as we learned in a previous video, that is the total effective transmission power of the entire device. So the device being the wireless access point, and its radio, its antenna, etc. So for each 6 decibel increase in EIRP, you're doubling the range. Now, even though this is the 6 decibel rule, remember earlier in the video, though, antenna gain is expressed as dBi, or decibels relative to an isotropically radiated source, and a theoretical radiated source such as the sun. And let's say, for example, in our situation here, we've got an antenna that is only 2 dBi. So it only has a gain of 2 dBi, not that strong, just kind of adequate, but people are complaining. So let's say that doubling the coverage area would be adequate. So that means that you would need to get an antenna that is 8 dBi. So 2 plus 6 is 8, you double the coverage area range. Now, the converse is true as well. Let's say, for example, you were to purchase an antenna that is 6 decibels less than what you have. That means that you're going to reduce the range of your antenna by half. Now, after you've purchased the appropriate antenna for your wireless LAN, there's a couple of things to bear in mind as to where you mount the antenna. Now, we talked about the placement of omnidirectional antennas. Ideally, they should be in the center of the room. But if you've got high-gain antennas, you need to keep them away from the users, meaning you don't want a really high-gain, powerful antenna right above a user or very close to a user that's just introducing far too much radiation, radio frequency radiation to a person, as it can be physically harmful. So you need to be careful about placing the high-gain antennas near people. Also, if it's an outdoor high-gain antenna, ensure that it's placed high enough above obstructions such as trees and buildings. Make sure that the Fresnel zone is relatively clear. If you are mounting the antenna indoors, make sure you keep that antenna as much as possible away from metal. Remember, metal is going to introduce a lot of multipath, and it's going to cause a lot of reflections of that radio frequency signal. So radio frequency signal and metal just does not mix well. So ideally you want to keep that antenna as far away from heating and air conditioning ducts, large steel ceiling beams, the actual building superstructure as well, major power cabling runs and things like that. Also, when you're mounting the antennas, bear in mind the antenna polarization as well. So let's say, for example, you're creating a point-to-point wireless bridge between two buildings, and if on one antenna you have a horizontal polarization, and then on the other antenna, on the other building, you have a vertical polarization, the throughput of that wireless bridge link will be drastically reduced because you have opposite polarizations between those two antennas. So make sure they're both either horizontal or vertical when they're being mounted. And with that, that brings us to the end. Let's bring up our whiteboard and do a recap of what we've learned in this video. So we start off this video by learning that there are omnidirectional antennas, such as a dipole antenna. Remember that radiates at 360 degrees on the horizontal plane. And there are semi-directional antennas, such as a Yagi antenna, and then highly directional antennas. So as we go through the different antenna categories, the radio frequency beam width essentially gets narrower and narrower, culminating with the highly directional antenna, which has a very narrow beam width, and the advantage of that again is to allow the radio frequency signal to travel very long distances. And we also learned about antenna concepts such as antenna gain, antenna polarization. So we learned that if the antennas don't have the same polarization, either vertically or horizontally, it has a tremendous effect on the throughput within a wireless network. So you want to ensure that the polarization ideally between not only the wireless LAN devices, but also the wireless LAN devices and the wireless stations as well, meaning the laptop computers and the desktop computers that have wireless network adapters. And we also learned about concepts such as beam width. We learned about the azimuth beam width being on the horizontal plane and the elevation beam width on the vertical plane. And we learned about path loss and the 6 decibel rule. And throughout this video we learned the best practices for the location and installation of wireless antennas. And with that brings us to the end. I hope that this video has been informative for you, and I'd like to thank you for viewing.